Right. Well, everyone, my name is Vince Vitro, and I'm a computational scientist here at the National Institute for Computational Sciences. Today, I want to talk to you guys a little bit about the many integrated core architecture, which exhibited in Intel's Xeon Phi coprocessor. Talk to you about what those are, how they work, how they can be used, what sorts of results we've seen with them. There's actually a series starting today. On Thursday, we'll be discussing offload mode, or sort of the accelerator type of behavior. Next Tuesday, we'll be discussing CPU mode, which is where it's kind of running standalone native mode. And finally, we'll be talking about some real-world cases and performance. Hopefully, you'll be able to join us for the whole series. So today, again, it's just going to be kind of an overview. I will be talking about things in terms of Beacon, which is a local Xeon Phi cluster. But these things would apply to Stampede at TAC, or the machine at LSU, or a machine that has mics on, or Z5s, I should say. So forgive me, I've been running around in this field since there was no name Xeon Phi, so occasionally I just use mic. But technically it's the Xeon Phi. All right, I do want to acknowledge that this the work that was done here was actually supported by the National Science Foundation, part of the project. So, of course, anything I say is all me. To give you kind of a general overview about the Xeon Phi, discuss the programming model. Again, when we talk about the coprocessor itself, about the Xeon Phi. When we talk about the architecture of the coprocessor, we talk about the mic. Discussing these mic programming models. I also have an overview of the Beacon system, which will itself in other ways to how we use it on other resources as well, and some role examples. Without review, just a little bit about the mic architecture. Not so much the Xeon Phi in and of itself, but the mic architecture, and has been throughout several development Intel products and will continue to be as Intel moves this line in the future. It is targeted at highly parallel work. This is not a machine that you're going to go, man, I just started this MPI code and wow, 60 cores. I should be able to get Ruby on that. It's something that you take great advantage of threading and vectorization in order to really get the performance out of the models and give context. Or they're taking great pains in your vectorization and use them even in an offload context. So you really want to have some mature application, or start completely. They are very power efficient. Okay, these cores do not have some speculative logic. They don't have some of the other aspects of the regular standard Xeon processor will have in it, and so as a consequence, it is lower power. It's also only 1 gigahertz, whereas the Sandy Bridge is 2.3 gigahertz. It's really 2.5 times slower per core. However, as posited here, it has has twice as many threads per core. Normally on a Sandy Bridge, you have 2 hardware context threads, and 1 arithmetic unit, 4 hardware context threads, 2 arithmetic units on each core. Lastly, you got a wider SIMD unit. The vector unit allows us to do up to, in this case, 16 double precision fuse multiply add operations in 1 clock. Is as big as the one on the Sandy Bridge, which one went to be 8. And of course, the smaller your variable type, the more of those you can cram into that SIMD. All right. One of the things that makes special, mic architecture, unlike a traditional GPU core processor, it can have pretty much autonomous, like a CPU. It runs full service Linux. It's SD or anything like that. It will do everything that your normal Linux distro will do. x86, all right, IEEE 754. Applications and all your normal coding languages. Okay. So, of course, all the stuff that you're used to, your libraries, your compilers, your vTune, your debugger, they work on it as well. That's a nice benefit. Okay. The coprocessor itself is a PCI bus accessory. You plug this in the PCIe card, and boom, off you go. Just like if you plugged in a graphics card or a work card or what have you. Okay. You of course deal with the depth of the PCIe, right? You have a super fast memory. This thing, all right? You have an inner core processor, an inter-processor communication network, and you have a fast processor and very fast memory, but you are kind of at kind of at the service of the PCIe bus. It can only go so fast, and that is the bottleneck, is back and forth between the PCIe bus and the processor. And we'll talk later about how different nodes can exacerbate that, mitigate that, depending on how you treat the program. Okay, so as I said, here you got this interprocessor network with coherent cache and all these vectorized cores. It's fast. It's just like running on any other, CPU, multi-core processor in that respect. Like I said, it's the fact that you don't have a nice direct access to the RAM. You've got to bounce through to get the system in. Now, of course, the mic has its own RAM, 8 bytes or 16. We have new models, 16 bytes. And that RAM is something that you use either in or offload and enable that situation. And anytime I go to talk to the CPU or do I/O, you got to proxy through that bus, and that is really powerful. This is a picture of the same exact thing I just showed you. That's a little more compliancy, perhaps. If you're interested in that, you actually want to know where the L2 cache is and where the RAM is, and where different things are. This is a nice, picture. Now, let's get to the good stuff. Vector processing. Vector processing. Those of you familiar with vector processing, if you weren't around back in the days of vector machines or have that beaten into your head by your graduate advisors, it's really pretty great. All right, what we can do is effectively have a vector of scale added and multiplied by two other vectors of scale, and you got with a result, all in one clock tick. Now, if it was just a vector of length 1, it's exactly the same as the scalar process. However, in this particular case, we have 512 bits. Right? So what can we fit in there? Well, we can fit 8 full precision words, 16 single precision, 32 integers. Obviously, the smaller the memory type or the type, all right, the better off that you are in fitting several of them in there. And again, it will do a fuse, multiply, add operation every clock. I say you can do up to technically 16 flops. That would be 8 double precision multiplies and then 8 double precision adds, all in one clock. Right. The kinds of processors that we have on Beacon, almost the same as those on Stampede and elsewhere, right? Now, the ones on Stampede are 7110Ps. They have one extra core and slightly faster memory, right? Their own RAM memory, obviously. PCIe is PCIe. So, but otherwise, they all work about the same. They're passive cool, right? Their peak is around a teraflop, all right? Your clock speed is right around a gigahertz. You have 16 gigabytes of memory. The memory speed on ours is 5.0 gigatransfers, a little faster on the ones with pack, right? And then you see memory bandwidth, cache, all that sort of information, okay? That's all interesting, but not particularly important to be able to use the architecture. Why in the world would we care? Is this just another fancy thing, or does this have a purpose? Well, it does have a purpose. right? The purpose here is multitudinous. There are several different ways you can get a lot of these plots, right? Obviously, you're looking at this diagram here, right? We go for multi-core centric, which is one. Let's talk about Sandy Bridges, 8 cores per die, okay? Versus Mike, all right, is 60 cores per die. You know, like it'd be an obvious choice, but we've already talked about the trade-off: power, predictive logic, slower clock speeds, less RAM, all these sorts of things. Okay, so what good can I get out of it to pass all those hurdles? Obviously, we all know how to use multiple. You think we either run multiple threads on a core, or some people do multiple NPI ranks on one process. And that's all well and good, and that's pretty much the traditional way that computing has been done. Even hybrid processes. You may have multiple NPI processes, a couple of threads of heaps. And that's one paradigm. Now, on the very opposite end of that, over looking at a situation where we're running natively on the mic, we'll again probably have multiple NPI ranks, possibly even more, because the memory per core is much lower, right? It's 8 gigs divided by 60 versus, in the case of Beacon, 256 gigs divided by 16 cores on the 2 Sandy Bridge sockets, okay? It's a difference in memory. You can decompose it slightly different. But let's say you put 6 NPI ranks on your mic. You still have 54 times 4 threads to play with. Right? In the Xeon, you have 10, you have 20 threads. You see what I mean, and that's total. I don't mean per NPI. Yeah, by NPI rank. And so again, you see what I mean by the limitation of just 1 or 2 threads maybe per NPI rank on those processors has been put out of the water on the mic. You don't worry about it. What to do is express significant parallelism, where you're going to get caught up in PCIe speed or the speed of each core. Now, obviously, the next step over for multi-core centric is offload. Okay, and the reason is as simple as you would think, right? If you're going to use the CPU, try to use the coprocessor, the accelerator, just like we've done with GPUs for years. Okay, and that is where you have a code that's mostly serial, but there are a few very highly parallel sections that will benefit a great deal from the vectorization, and so on and so forth, and the like. That's to the point where you can analyze the cost of transferring things over that slow PCIe link, the speed gain by doing computation at double speed because of the vector unit, or at many, many orders of magnitude more threads. Okay. Of course, you have symmetric. Symmetric mode is kind of in the middle. All right. You may have some of your work being done on the mic, some being done on the Xeon. You have it such that all your work is being done on the Xeon, but you're offloading portions of it to the mics. You have some mics running in native mode along with that, depending on how task parallelized your code may be. Offload is not supported by direct, right? Code that is extraordinarily parallel, but has a few phases of serial that is very dependent on predictive logic and things like that don't exist on the mic, and so it might be helpful to have this has been left off of very many people's diagrams. I still think there's probably a code or two out there that might be able to utilize it, so I mention it. It's not supported by directive, it's not in documentation really. It's one of the sort of academic cases. But we all know that those occasionally pop up. Again, let's discuss programming paradigms, at least in terms of the plans I'll be using. All right, first thing, native mode. Again, native mode, I'm talking about using the PHY just as if it was a CPU. All right, you have it running on the mic. Either you have it mounted to Lustre, or to, in our case, on Beacon, we have a terabyte SSD on each node. You have something that mic actually mounts. It does not mount home, just as most good compute nodes should not mount home. you have your Lustre system or the local SSD that you can take and put everything on, and then it will either be accessed to mic, or you can even copy things directly into the mic to random memory, or just to hang out. Now, what happens is if you have to copy something onto the mic and call it out from Lustre, call it out from the SSD, you take away some of the RAM memory that you would have had otherwise. And 8 gigs with 60 cores instead of premium. You really want to do that if you can avoid it. Our proxy through the CPU. There is movement in the Zappitch and Intel MPI community to do more mic direct sort of communication, similar to the GPU direct that we've seen with NVIDIA. Trying to put that together. Obviously, we've seen that those are all a little slow and tough because there's a lot of patience. We're running on the mic and only the mics. Okay? You're running a host. The fact that your mic is obfuscating you completely, other than the fact that when you file the code, and it's going to run on the CPU, except where it can offload to the mic. And if there, it just goes, oh, I don't have any mic, so I'm just going to run all of it on the CPU. Okay? So the thing about offload mode, the thing that kind of makes it simple, is really obfuscated to the user what you really need to worry about. All you have to do is compile it and ./a.out, and you're good. What it does is stuff over the mic, it's under the covers, we can have report that to you, but it's not necessary. Or it keeps it on the CPU. But kind of the simplest, most robust method, because you always call that to the CPU. Okay? You want to be able to offload it, because you'd love to be able to have 100, 200 threads if you've got enough work. Okay. You only explicitly copy things back and forth, just like on the GPU, right? I need you to have this array, and I need you to send it, take the values in, spit them back at me. I need you to maybe not copy anything here, but just allocate memory, and I'll be using it, and I don't need to worry about it off the mic. There are lots of different options, and we'll talk more about that when we actually do put our tutorial on that. What's crucial for you to understand is that everything can be done explicitly. Implicit, where you declare the variable that's sort of a shared variable in the mic and the Xeon Phi and the Xeon, only works with C and C++. And what it effectively stores both variables in both locations and updates them in between each offload. Only update things that change. So it can actually be quite efficient to utilize. However, it only works in C, C++, and you have to be very careful about variables in and out of scope, right? I mean, if you're not careful, it may have changed on both the host and on the mic, and then it doesn't know which one to keep. Well, what it do is just it's going to keep the last one it got. It might work out for you under certain circumstances, and then it might run it with a different set of parameters, and to the last one is a different processor for your answer. Right? So be cautious and cognizant when you're doing things like that, just as you would be if you were running anything with multiple threads. Okay? Execution. And this is one crazy old bird of you got native mode, you may have some offload mode, run together, you may have some mics that are just running things, some CPUs that are just running the code, and other CPUs that are offloading the mics, these mics are just being used to offload. Again, you may have multiple different tasks that need different combinations of the processor and coprocessor. And that gets option. Okay? First, you have MPI, OpenMP, hybrid. And that is a method that shows probably some of the most promise for the Xeon. The main reason for that is the fact that you can use that to further decompose the problem. That's great. And then you can P to take advantage of, now you basically increase your surface to volume ratio, right? You've got more communication to do, you've got smaller partitions. But they'll make up for that The fact that underneath those several frames, there are operations that are easily threadable and can be done, 100 quicker. You make, twice as much communication, computation is 100 times faster. Right? If you can do that, you've got some reasonably embarrassing parallel computations. So again, it's all about the trade-off, but generally speaking, you can kind of figure out from the get-go if the trade-offs are going to work or not, based on some back of the napkin kind of calculations. This is how many elements have, how big a vector unit is, this is how many clocks it's going to take, this is okay? So, a little bit about Beacon. Beacon in and of itself is 38 compute node Ash Cray. Now, we bought it with Zapro and delivered it cluster solution. They are equipped each with two 8-core Sandy bridges, right, at 6 gigahertz. These are actually legitimately 2.5 times faster. We have 256 gigs of RAM per node. Xeon 5. So you see a situation here where you could very easily take a great deal of advantage of the accelerators because you have 4 of them. Right? You have 2 hanging off of one socket, 2 off of the other. As long as you're careful about your process pinning, you can make some massive strides. Right? There are cores on one and 8 gigabytes of RAM. Right? So the idea, that's what we're working on. That's what we'll be doing in example on. We'll do this tutorial on this today. All right, so we've got this. And if you are a Beacon user or going to be a Beacon user, you access it through your EP like your other internet system. We have 4 mic cards that are, in this case, Night Core was the most recent incarnation of the Intel Xeon 5. But again, 4 of them C index because we're C machine there. Right? One thing that's very important is that with Beacon, they have an X server installed. Okay, we can actually tunnel it from the compute node out to the login node into a debugger. So this is actually no longer totally true. We do have DDT and we do have total. We do V as well. When you log into Beacon, it's just like a system. The environment should be in place. Obviously, the only compiler that supports the Xeon 5 at the moment is the Intel compiler. Right? Best you do your compilation on login nodes, simply because as long as it's not a crazy, long, painful, soul-sucking kind of compilation, right? To reduce the amount of time that nodes are taken to one person. Node modules, we have a lot of software that's available to you, and by and large, folks, if you have a piece of software that you're using, minus M or a flag in the compile and linking line, and boom, you can, it's compiled for the mic now. So if you have mic code or Xeon code, if you wanted to run a native mode, and let's say you use the FFPW library. Well, we have Beacon, and we've compiled them for the mic. You can think in your home. Right? You get that. You even actually have access to all the nodes that you request just by SSHing back and forth to all the nodes. You have a mic at that time. Just like most of our systems, you can use the submissions. All right. Again, when you are referencing this hardware, this is based on Intel sort of desired parlance. And this for any time you reference any kind of hardware, Xeon hardware. Now, you have to look at what your machine is. If you're talking about the mic, you're on Beacon, they're the Intel Xeon 5 5110. If you're on Stampede, Then you have 7110. So, all right, we use E5 2670. They are sandy bridges, but they prefer that you don't use the code. Okay. Your particular Xeons on the machine you're running on might be different. And this is great for all this with tech code. As a first reference, you don't need to put the registration and trademark. But these are the things if you're writing a paper on this that Intel appreciates. I'm going to talk a little bit about some results. Before I do that, understand the methodology for comparison. On the side, compared to the Xeon, we need to make sure that a few things are considered. One, we got to run the same code on both. There's nothing more useless than some optimization metrics where they say, I ran this code and then I code 100 times faster. Well, I use an accelerator. Well, that's good. I can see that helping. 100 times seems a little high. Oh, yeah, and I also completely changed the algorithm. Well, no, right? If I put a V8 Hemi in my 1972 Ford or my Ford Focus, it's going to drive a lot faster than the four-cylinder, right? And that's just common sense. So you apples to apples comparison. And so things to be run on both. Okay. So in order to make sure the hardware is comparative, we have two sandy bridges to one Xeon 5. All right. Well, one, the power draw is about the same between two sandy bridges that are on our system at least are 125 watts, and one Xeon on our system is 255 watts. All right. You have smaller vector units, so to really be fair, you got to compare against two sandy bridges and one Xeon 5. All right. It's really just attempting to give the sandy bridge and the Xeon 5, I should say, as equal footing as possible to start with, and see if you're really taking advantage of the threading and the vectorization really makes the 5 powerful. Okay. Like I said, how do we make it worth our while? More threads, program versatility, right? Larger unit. Those things that make the Xeon 5 great. Those things that your code over should be pretty easy. And the things that you've not considered before, you can still, it's just compile and run on the Xeon 5. There's not a whole lot to do with porting. It's actually going to run very well, because you've got to take advantage of some of these things. Otherwise, what you're doing is you're running it on a really fancy thing. Okay? Some of the different things that we've investigated at ACE, I used ACE the first time here. I just plan to application that is in it, that we work on primarily. Some of the things we've looked at are atmospheric modeling codes, astrophysics codes, CFD codes, earthquake, magnetophysics, tokamak plasma, agent-based modeling. Where you see ported, literally just means you recompiled it and ran it and tried to run it in a smart way to give us the most benefit. Run it with lots more MPI ranks and tons of threading and things like that. Then we've actually optimized in the code. We've gone in and utilized, and you'll see some results Enzo and H3D in the CFD code specifically, that we've optimized some parts of the code on the fly, better on the fly than otherwise. All right, so the first code we were using is Enzo. Enzo was written by the late Dr. Robert Hartnett, and is a very large, very well-known physics code. It is vector and has a hybrid API OpenMP programming, so it was screaming out for the fly. Okay. Now, it also uses third-party libraries, HDF5 and Hyper, which will recompile to the fly. And we do multiple MPI tasks for full processor and use for MPI tasks. That is what this code does best. So, look here, there's two different portions of this, all right? When is enzo C, where it's generating the case, okay? And UPL speed up should be what the speed actually was. It's very close, okay? And that's all well and good, but it doesn't really say anything about how it would compare to doing it. Same, all right, in this particular case, you get the bigger the problem that you're trying to decompose, bigger the mesh, right? The better your timing. But again, we compare it against the same. This just shows that the phi is scalable, like you would expect it. Okay, put it at H3D. Okay, 3D is kinetic simulation of the Earth's magnetosphere, which actually allows us to do some fluid hydrogenating, as they call it. All right, and it allows us to do things that are including ion kinetic effects, and it also has some really nice code that's been done in there as well, specifically the dynamic load model on something like that. Wow. At it. These that are a little high on the dotted line, it's just a rounding issue. But we were able to get about observed and about the ideal speed up. We were able to observe about the ideal speed up going from the number of MPI processes up. Now, I should point something out. You would not have 64 MPI processes. 60. This is actually 60. Which is, that's where the 64 ends. You would have MPI processes on a regular infinity grid. So there is something to be said. If you can perfectly out on Z, fine, good thing. But again, still haven't really shown you. All right, that's where we're coming with this. This is the Boltzmann equation, computational fluid dynamics solve. Boltzmann equations is a kinetic model. All right, therefore you have all these little particles banging around each other, and they're all kind of independent. And so you have something that's really vectorized and readily spreadable. All right. So here, all this is just the problem we did. One of these Couette flow. Just to give you an idea of what we're talking about with the Couette flow, you're looking at a situation where one plate is not moving, the other plate is moving. There's a gas in between them, right? And so you see this is the difference in velocity at steady state. And this is the temperature at steady state, obviously the highest temperature being in the middle, the lowest temperatures being up against the wall. So we took this software, several different optimizations. Loop vectorization. All right. Instead of using structures, all right. In very, very, very specific about you want to use an array structure, not a structure of array, and it's due to contiguity. All right. You remember it to be as contiguous as possible. Data for situation, and you can also align the data to its specific buffer length, so you know you don't ever cache it. You don't get as many the number of parallel sections. The spawning is much faster spawning and killing threads than on it. But all right, that you do, the less overhead you incur. Still pretty straightforward. Also should cut something. The phi is about 5 times slower memory allocation than the Xeon. And that's why when we talk about offload, we're going to talk about asynchronous memory allocation. Right? That slowness, you're going to actually want to see if you can do some of that work while you use doing other things that are useful. Okay? So another optimization is dependency. Right? Obviously, anytime you can avoid critical sections, that's a win. Under circumstances, you can use less precision, right? 1.4 is 1.4. It's not 1.3 399988724. It's 1.4. You know it's 1.4. Just use precision. Don't use double precision. You need all precision. Okay? Anytime you can do that, you can fit more things, items, variables, bits, pieces, what have you, in the vector unit. The more bits, the quicker you can compute. Right? And last week there was some compiler hints. Okay? To see pragma sin d. Pragma I depth says, hey compiler, I believe you can vectorize them. If there's any doubt in its mind at all, it's going to go, no vectorizing here. Okay? But I don't care if you have some doubt in your mind. I know that this is okay, that nothing's going to get clogged. Right? In that case, you can put a pragma sin d, and it will vectorize that regardless of what you think. Now, if you were wrong, you could get some bad answers. But seriously, if you're of what you're doing, can override the compiler. You see the relative speed up between the baseline version and final version. All right, we ended up getting about 7 times faster through these optimizations. It's pretty awesome. But you can only see the ones that made the biggest difference. The biggest were loop vectorization. Not a huge shock, right? Vectorization is pretty big. And then changing things to some things that you could to single precision. All right? Big difference there. Big jump. Right? That's a function of how much benefit you can get out of the vector unit, and the threading on the phi is the thing that's going to decide whether or not that's what you want. So you're still going, did you try to lose? I still haven't seen anything with the Sandy Bridge lose. I have to get there. Okay? So we have relative speed up. All right? And this is not quite that plot. In the sense you see that the Xeon, all right, on right here with the squares, it actually, it's a little bit faster, right? All the way up till you get to 32. Actually, 16 is nice and linear, right? Because you have 16 cores each with 2 threads, but only 1 arithmetic. So up to 16, you can scale nice and linearly. When you get to, you've kind of done some hyper-threading, so you've got to be a little bit wary and know that you're not going to get a perfect linear speed up. And you continue to get speed up on the Xeon Phi all the way up to 4 times 61. In this case, because these were a different rev processor, they had 61 cores. All right. Notice it doesn't go perfectly linearly because after you get past 120, you use all the, each of these cores has 4 hardware threads and 2 arithmetic. 22, in this case 122, utilize all the arithmetic. So from there on hyper-threading, and that's why you see the slope go down. Again, showing you that it's fast. This show you that it's just, and of course you're going, oh dude, I can't do that. Max things out, the VGK solver, all right? I'm out, the fastest I can get it to run is slower than if I max things out on the Xeon Phi. This is in native mode, okay? So this is proof that even though the core, either some barriers to entry, once you try, if you can vectorize and you can thread, you can beat the same. Well, you might be spending all this effort to beat it by a little. Well, you have to look into the future. That's one thing. The cost and the power footprint of the Xeon Phi are orders of magnitude less than the Xeon. And that's what we're considering as we run up to our 30 megawatt limit. Okay? So almost done here, and then I'll take a few questions. If you get onto Beacon or any of these like resources, the Intel compiler suite, the studio that they've given us, they're examples. And in Fortran, those are great to look at, great to play with, great to learn. We'll be using some of those in later tutorials. There's a site, soft/Mike developer, that has a ton of documentation. You have to be a little bit wary of when it was published because things change with the Mike software stack. Free because it's so new. Of that. But otherwise, you can find some pretty good information on forums, especially. All right, again, you've got questions on using Beacon, or you've got questions about using Beacon. You can help at next.uck.edu. They'll try to get you sorted out. So I thank you for your attention, and I will be quiet, and I will take any questions you all may have. You know, you have a nice config file, Cray XT5 and a Cray XT7, and and that Dell whatever, and so on and so forth. Very rarely do they have the version. However, it is as simple as giving -m compile link lines. The thing I've always found gave me the most trouble was on trying to get it to configure, be happy about cross-compile. Sometimes you're going to do that and others. In order to make sure that -m might propagate all the way down into all the make files, all the sublines. That can be difficult. And I've had to go in a few times and trick the code into believing other things so that I could find where it was creating this one dumb make file that just wouldn't give me a -m mic. The only had issue, and it's no longer the situation, was I just recently made global, all right, 5.2 for the mic, and 5.2 I was having a lot of difficulty, not because of 5.2 so much, because when I was trying to do it, and it's difficulty because it in MK libraries for the mic did not have all the blocks, the pack, the scale pack functions that were needed global array. The global array wanted to go its own blog, the pack, and scale pack. And I could, the life of me, figure out how to tell it to do that for the mic. But when they came out with the Yocto library, all functions are now supported. So however, it's not too bad. These hiccups, just like there would be compiling those. Yes, exactly. And make files and big files are still a little bit of a dark art. Right? Why is it I know asked Intel when we did that, we're like 60? 61? Like, so used to always being in powers of 2, right? It's percent due to the form factor on the die. Apparently, and I'm not a microchip producer, but from what they said, get a die is getting 61. And so if I get less, maybe it only doesn't work 75% of the time instead of 95%. Some of these that have these little flight changes are just a function of it's a little harder to make this file, so it costs a little more. Now, if you really get out of that extra 4, just one extra 4 out of 61. The thing that I have been told that I kind of lend to is when you got OS working on one of them, at least one of them. And like this, you're going to have one core that often is sucked into doing OS tasks, system tasks. If you want, you can just work with 60 cores and just see that other core with this new version. And that 40 is a nice number to work with. Whereas on 60 cores, that one core only has 50 miles. That's not quite as pretty. So that's the only thing that I've ever heard that has any specific trees, but it makes a significant difference in the performance. Just make sure you're computing things up a little bit. Anybody else that's online have any questions? Then unmuted. Awesome. All right. Well, that was perfect. Just in time.